Wait, so picture the scene. It's late afternoon on the shop floor. You've just finished a massive production run, let's say 500 units.
Oh, I know this feeling.
And the CNC machine, it's been humming along perfectly for hours. You know that sound, right? That rhythmic, hypnotic hum.
Yeah.
No alarms, no weird crunching noises. You are feeling good.
You're already mentally spending that bonus check.
Exactly. On a vacation, maybe? And then the quality inspector walks over, and they are definitely not smiling.
And my stomach is already nodding up just hearing this.
They're holding a pin gauge and a micrometer, and they look frustrated. They tell you they've had to reject the entire batch, every single part. The holes, these simple tiny holes you drilled, they're oval, or they're rough inside, looking like a plowed field, or they're just slightly off-center.
That is the absolute worst feeling in manufacturing. It is a literal gut punch. You go from hero to zero in, what, 10 seconds?
And suddenly, you're in a nightmare. You have a pile of expensive scrap metal, a deadline that just flew past you, and a boss breathing down your neck. Now, be honest. What's the first thing you do in that moment?
You blame the code, 100%.
Right. You look at the G code. You think the controller messed up. Or, who wrote this program? Did I miss a decimal point?
It's the natural reaction. I mean, we trust the steel, so we blame the digital. We assume the machine is this perfect robot, so the instructions must be wrong.
But today, we're going to flip that assumption completely on its head.
We are. We're doing a deep dive into some serious technical insights from JM's CNC machine. And their core message is, well, it's going to hurt some feelings, but it's necessary. The machine is usually innocent.
Innocent. That feels like a bold claim when I'm looking at 500 bad parts.
Mostly innocent. I mean, it's just following orders. The reason those holes failed isn't usually a digital glitch. It's a failure of physics. It's purely mechanical.
So that's what we're unpacking today, the physics of the perfect hole. We're going to look at why drilling, which seems like the most basic, intro to machining 101 operation, is actually this violent battle against stability, resonance, and geometry.
It really is. We think of drilling as just poking a hole, but at the microscopic level, it's chaos. If you don't manage the forces involved, you get what we call the four enemies of the perfect hole.
I love that we're personifying them. It makes it feel like a battle strategy video game.
It is a battle. You're fighting drill walk, spindle runout, exit burrs, and internal chatter.
Okay, so our mission today is to arm you, the listener, with the physics hacks to defeat these enemies. Whether you're running a Haas VF2, managing a shop, or you're just someone who loves understanding how things are made, this is about what's actually happening at the cutting edge.
Precisely. It's about moving from hoping it works to knowing why it works.
Let's start at the very beginning, the moment the tool touches the metal. The article calls this first enemy drill walk. Now, to me, that sounds like a dance move from the 1950s, but I gather it's much more destructive.
Much more destructive. Think of it as the drunken start.
The drunken start. Okay, set the stage for us. What's actually happening there?
So you program the drill to go to a specific coordinate, XYZ.
Yeah.
The machine moves there perfectly. The servo motors are locked in. The readout says you are exactly where you need to be.
Right.
But when the drill tip actually touches the surface of the material, it doesn't bite in immediately. It skids.
It skids like tires on black ice.
Exactly like that. It slides sideways across the surface of the workpiece before it finally digs in. By the time it actually starts cutting the hole, it's not where it's supposed to be.
Oh, wow.
It might only be off by a fraction of a millimeter, maybe 50 microns, but in precision manufacturing, that part is ruined immediately. The hole is technically straight once it gets going, but it started in the wrong zip code.
That is wild. So the machine thinks it's in the right spot. The readout says it's in the right spot, but the drill itself has gone rogue.
Yep.
Why does it skid? I mean, these are sharp, hardened steel tools spinning at thousands of RPM. Shouldn't they just pierce right through?
You would think so, but this is where we have to look at the actual geometry of a drill bit. If you look at the very tip of a standard twist drill, let's say a standard 118-degree point angle,
Okay.
there's a spot right in the dead center called the chisel edge, or sometimes the web.
The chisel edge. Okay, I'm visualizing the tip.
And here's the secret that messes everyone up. The chisel edge doesn't cut.
Wait, the tip of the drill doesn't cut. That seems incredibly counterintuitive. What does it do then?
It creates pressure. The cutting lips are on the outside. The very center point, it's blunt, doesn't slice, it extrudes. It pushes material out of the way like a plow.
So it's blunt force trauma.
Basically, yes.
Yeah.
So imagine taking a blunt plow and pushing it hard against a smooth, flat piece of steel. It can't find purchase.
It's just sliding around.
It's spinning, sure, But the rotating forces are actually creating instability. It's looking for a weak spot or a divot to enter. Until it creates that divot, it wanders.
So it's wandering around looking for a door, essentially.
Exactly. And that wandering is the walk. And it's even worse if the drill has any manufacturing defects. The source points out that if the two cutting edges aren't exactly equal in length or height, even by a tiny amount, the drill will physically push itself away from the stronger side.
So it's practically fighting itself. It's unbalanced.
Correct. And that lateral force pushes it off-center before it even enters the part.
Okay, so how do we stop the skid? How do we give it that purchase so it starts exactly where we told it to?
The article suggests a couple of things, but there's one gold standard solution. You can't trust a standard drill to start itself on a flat surface. You have to give it a path to follow.
You need a pilot hole.
You need a pilot hole.
Yeah.
Exactly. You use a spot drill or a center drill first. These are short, extremely rigid tools. Very short flutes, so they don't flex, they don't walk. They just come down, make a tiny, perfect divot, usually just deep enough to match the diameter of the chisel edge, and then retract.
So you make a little dent, and then the big drill comes down, sits in that dent, and literally cannot go anywhere else.
Exactly. It centers itself immediately. No skidding. The physics of the chisel edge doesn't matter anymore because the path is already broken for it.
Got it. Now, what if you're in a hurry? What if you're doing a high-speed production run and you don't have a tool changer slot open for a spot drill?
Then you have to pay for better tooling. The source mentions using high-rigidity solid carbide drills with what they call split-point geometry.
Split point, is that what it sounds like?
Yeah. If you look at the tip under a microscope, you'll see they've ground away that blunt chisel edge we talked about. They thin the web right down to a point.
Oh, interesting.
It makes the tip self-centering. It acts more like a needle than a plow. But even then, the source warns about setup. If your clamping is loose, if the part vibrates even a tiny bit when the drill touches it, the drill is going to walk, no matter how fancy your geometry is.
So, lock it down or lose the part.
Physics doesn't care about your deadlines. If the part moves, the hole moves.
Okay, so let's assume we've survived the start. We used a spot drill, we're locked down, the drill has entered the material perfectly, we're feeling confident, but now we run into the second enemy. And this one sounds physically impossible to me. The triangle hole.
Ah, yes, the lobed hole. This is a classic how is this possible moment.
The source describes measuring a hole with a pin gauge, which is a perfectly round cylinder. It fits in one way, but if you turn the gauge or measure across a different diameter, it doesn't fit, because the hole is egg-shaped or triangular. How does a spinning round drill cut a triangle? That sounds like magic.
It isn't magic, it's spindle runout. And honestly, it's probably the most common cause of mystery failures, where operators just scratch their heads and swap tools endlessly.
Okay, unpack runout for us. We hear that term a lot in machining, but what does it physically look like?
So, in a perfect world, your spindle spins the drill perfectly on its axis, like a spinning top that's perfectly asleep. Zero wobble. But in the real world, bearings wear out. The taper inside the spindle gets dirty, or the collet, the thing holding the drill, has a piece of chip stuck in it.
So the grip isn't perfect.
Right. So the drill isn't just spinning, it's orbiting.
Orbiting, like a planet going around the sun.
On a microscopic scale, yes. The center of the drill is moving in a tiny circle as it spins. So think about what that does to the cutting action. The drill isn't acting like a drill anymore.
That's a doing.
It's acting like a boring bar.
A boring bar. That's the single point tool used to widen holes, right?
Correct. Because of that orbit, the effective cutting diameter is larger than the actual drill. So first off, your hole is oversized.
You've got a bad start.
Right. If you're trying to hold a tight tolerance, you've already failed. But here's where the triangle comes in. Because the tool is wobbling, it's not stable. As it hits the metal, it deflects. It creates a rhythmic pattern. Yes. It bounces, it cuts, deflects, bounces back, cuts again. This often settles into a three-lobed pattern. It's a shape of constant width, like a rouleau triangle. So if you put a caliper on it, it might measure correctly, but it's not round. It won't accept a round shaft or a bearing.
That is fascinating.
Yeah.
So the wobble creates a geometric pattern that carves out a polygon.
It's geometry in action, and the source gives us a very specific, terrifying threshold here. It says if your radial runout exceeds 0.02 millimeters, that's 20 microns, you are in trouble.
0.02 millimeters. That is tiny.
It is about the thickness of a human hair, maybe less. If you have more wobble than that, it is almost impossible to hold tight tolerances. And it isn't just about the hole shape. Think about the tool itself. If it's orbiting, one side of the drill is smashing into the wall harder than the other side.
So you get uneven wear. One lip of the drill is doing all the work.
Exactly. Which creates more vibration, which leads to a worse finish. It's a downward spiral. You'll wear out drills twice as fast and make bad parts the whole time.
So how do we fix it? We don't just throw the machine away.
Hopefully not. First, you have to measure it. You get a dial indicator, put it on the tool, and spin the spindle by hand. See if the needle moves. If it moves more than that 0.02 millimeters, you have a problem.
And if it does?
Check the basics first. Clean the collet. Clean the spindle taper. But if the runout persists, you need to look at the tool holder itself. The source recommends switching to high-precision hydraulic chucks, or shrink-fit chucks.
I've heard of shrink-fit. That sounds intense.
It is. You use an induction heater to heat the tool holder up to a high temperature. Metal expands when it gets hot, right? So the bore opens up. You drop the tool in. Then as it cools down, it shrinks. It grips the tool with incredible uniform force across the entire shank.
So there are no moving parts, no screws, no collets, just metal gripping metal.
Exactly. It's extremely concentric. It stops the orbit. It essentially fuses the tool to the holder. It's the closest you can get to that perfect world rotation.
I love that. Using heat to lock in precision. Okay, so we've drilled straight using a pilot hole. We've kept it round by eliminating runout. But now we're approaching the bottom of the part. We're about to break through to the other side. And this is where the third enemy is waiting.
The exit strategy, as I like to call it.
The source paints a pretty nasty picture here. It says the hole can look perfect on top, smooth all the way down, but on the bottom there's this jagged metal cap or a crown just hanging there.
The exit burr. And that crown is expensive because now someone has to manually deburr it. That takes time, money, and risks scratching the part.
Why does it happen at the bottom and not the top?
Physics again. Think about the material underneath the drill tip. When you start drilling, you have the whole block of metal supporting the cut. But as the drill gets close to the bottom, the amount of metal left underneath the tip is getting thinner and thinner.
Like the ice is getting thin.
Right. Eventually, that layer becomes so thin that it loses its structural strength. It can no longer support the force of the drill pushing down on it.
So what happens?
Instead of the drill shearing or slicing off the metal like it did in the main body of the hole, it starts pushing it.
It punches through.
Exactly. It acts at a punch. It extrudes the metal out the back. This is called plastic deformation. The metal stretches and tears instead of cutting cleanly. This creates that jagged cap. And this is way worse in ductile materials, stuff that likes to stretch, like aluminum, copper, or 3/16 stainless steel.
That makes total sense. It's like when you're poking a pencil through a piece of paper. If you do it slow and the paper's just hanging in the air, it tears. But if the paper's supported against a table, it cuts a clean hole.
That is a great analogy. Paper in the air is exactly what the bottom of your part is. It's unsupported.
So how do we solve this? We can't change the material physics.
No, but we can change how we treat it. There are two main hacks here. First, the parameters. The source suggests a very specific pro move. You need to reduce your feed rate by 50% just before the drill breaks through.
Slow it down.
Slow it way down. Not the RPM, but the downward speed, the feed. Yeah. By reducing the feed, you lower the axial force, the downward pressure. This stops the drill from acting like a punch. It gives the sharp edges time to catch up and slice that final, flimsy layer gently.
Smart. It's about finesse at the finish line. Don't sprint through the tape.
Exactly. And the second solution is pure mechanics, going back to your paper on the table analogy. Use a sacrificial backing plate.
Explain that.
You clamp a piece of scrap material, aluminum or mild steel, directly underneath your workpiece, tight against it.
So the drill thinks it's still cutting?
Yes. The material never gets thin because there's something solid behind it. The drill cuts all the way through your part and into the backing plate. The pressure remains constant. The exit burr is practically eliminated because the material was supported the whole time.
Simple, but effective. I guess the only downside is you burn through some scrap material, but that's cheaper than paying a guy to file burrs for an hour.
Much cheaper.
Yeah.
And better quality. It saves you from that hanging crown disaster.
Okay, we have one final enemy to discuss, and this one isn't about shape or burrs so much as it's about the experience inside the hole, the sound of failure.
Chatter.
Chatter. The source says if you look inside a hole with a flashlight and you see lines that look like a vinyl record,
or rough spirals,
that's chatter. And apparently you can hear it happening.
Oh, you can definitely hear it. If you've spent any time in a shop, you know the sound. It's a distinctive screeching or hammering noise. It sets your teeth on edge. It is the sound of instability.
What causes it? Is it just the tool being loose?
It's usually vibration, but specifically regenerative vibration. The source uses a great analogy, the tuning fork effect.
Okay, explain that.
Imagine holding a drill bit. If it's short and stubby, it's rigid, it doesn't want to bend. But if it's long and thin, let's say 10 times its diameter, and it's hanging way out of the holder, it's flexible.
It becomes a spring.
Exactly. When the cutting forces fluctuate, which they always do, that long drill starts to vibrate. It resonates. And as it vibrates, it's banging against the walls of the hole as it cuts.
Banging against the walls. That sounds violent.
It is. And here's the regenerative part. The drill vibrates and cuts a wazy surface. Then, on the next rotation, the cutting edge hits those waves, which excites the vibration even more. It amplifies itself.
Oh, wow.
That's what creates those vinyl record grooves. It's literally a record of the vibration frequency.
So the drill is bouncing around inside the hole, carving its own instability into the wall.
Another cause is chip clogging. If the chips can't get out, they pack into the flutes, then they start rubbing against the wall. That friction creates vibration too. It's like trying to run with rocks in your shoes.
So how do we silence the chatter? How do we stop the tuning fork from ringing?
The first rule is geometry. Shorten the overhang. Use the shortest drill possible for the job. Don't use a long drill for a shallow hole just because it was already in the machine. It's just asking for trouble. Stiffness drops off dramatically as length increases.
Makes sense. Stiffer is better.
Second, break the resonance. Chatter often happens at a very specific speed. It's a harmonic frequency. Sometimes, surprisingly, simply changing the spindle RPM, speeding it up or slowing it down, can snap the system out of that resonance zone. It stops the vibration instantly.
That's a cool trick. Just tuning the radio, essentially, until the static stops.
And finally, for the chip clogging issue, the source recommends using a specific cycle, peck drilling.
Peck drilling. That's G83 in the code, right?
That's the one. Instead of drilling in one continuous motion, the drill goes in a little bit, pulls out completely, goes back in, pulls out again.
Like a woodpecker.
Yes. Every time it pulls out, two things happen. First, it breaks the chips and flings them out of the hole. Second, and just as important, it allows coolant to rush into the hole and hit the tip. This reduces friction, reduces heat, and stops that packing that causes the vibration.
It seems so obvious, but I bet people try to rush it. They just want to drill straight through to save time.
All the time. Pecking takes longer. It adds cycle time. But if you save 10 seconds on drilling and spend 10 minutes deburring or polishing out chatter marks or scrapping the part because the finish is bad, you haven't saved anything.
That is the truth. Manufacturing is always a balance of speed and risk.
So if we look at the big picture here, we've gone from the start, where we have the drunken walk,
to the middle, where we have the orbiting triangle hole,
to the violent breakthrough with the exit burr.
And finally, the vibrating, chattering finish. We've covered the whole life cycle of a hole.
We have. It's quite a journey for such a simple feature.
And what stands out to me is that none of this was about the software, really. I mean, sure, you use G83 for pecking, or you program a slower feed rate at the end, but the root problems were physical. It was about stiffness, geometry, heat, and leverage.
That is the big takeaway. A failed hole is rarely a computer error. It is a failure to manage physics. The machine is rigid, sure, but the process is dynamic. You're trying to force a piece of metal through another piece of metal. Things want to bend. Things want to vibrate. Things want to get hot.
Yeah.
Your job is to stabilize the contact, maintain concentricity, and manage the violence of that breakthrough.
Manage the violence.
Yeah.
I think that's going to be my new mantra for manufacturing. It's not just pushing buttons, it's containment.
Absolutely. When you look at a CNC machine, it looks so solid. It looks like a monolith, a slab of iron. But when you get down to the 0.02 millimeter level, everything is flexible. Everything is alive, in a way.
That leads me to a thought I wanted to leave our listener with. We've been talking about drills acting like tuning forks or boring bars, just based on how you hold them or how fast you spin them.
Right. The tool changes its nature based on the conditions.
Exactly. So if a simple, solid steel drill bit can behave like a flexible, organic system wobbling and vibrating, what other parts of our rigid manufacturing world are actually behaving like organic systems when we aren't looking?
That is a provocative question. It changes your perspective.
Think about the machine frame itself, the floor it sits on, the fixture holding the part. Are they really solid? Or are they all just humming along, vibrating at their own frequencies, affecting your quality in ways you haven't even measured yet?
If you start thinking like that, you will never look at a factory floor the same way again. You realize nothing is truly static. It's all moving.
It is. And that is why you need to measure your runout.
And keep your edges sharp.
Exactly. Thanks for diving deep with us today. Go check your chucks, watch that feed rate on the exit, and we'll see you on the next one.
Safe drilling, everyone.